Welcome to the Explainer. Today, we're diving into one of the most powerful and, let's be honest, often feared features in programming, C++ pointers. So let's just get right to it with a little question that really gets to the heart of why they can be so tricky at first.
All right, let's kick things off with a little puzzle that trips up so many people when they're starting out. Say you have an integer pointer, we'll call it PTR, and it's holding memory address 100. So, what happens when you increment it? Your gut reaction is probably 101, right? But the real answer? Well, that's where the magic of pointers really begins.
Believe it or not, the answer is 104. And the reason for this is absolutely key. See, this pointer isn't just pointing to a single byte of memory, it knows it's pointing to an entire integer. And on most computers, an integer takes up 4 bytes. So when you tell it to go to the next one, it knows it has to jump forward 4 whole bytes to land on the start of the next integer.
And this gets us to a really core idea, the pointer's unit. It thinks in chunks, and the size of that chunk is just the size of whatever data type it's pointing to. That's exactly why you have to declare what type of data your pointer will point at, whether it's an integer, a character, whatever. It tells the compiler how big of a step to take every single time. It's what makes pointer math so smart.
Okay, so now that we've got a handle on how pointers actually move, let's put them to work. We're going to see their first real superpower in action by tackling a classic programming problem.
So imagine this. You want to write a simple function that swaps 2 numbers. The most common first try is what you see on the left, call by value. We pass our variables a and b to the function. But now look at what's happening in memory. The function just makes its own private copies, x and y. And yeah, the swap works perfectly, but it's only swapping the copies. The original a and b, they're back in the main program, completely untouched, as if nothing ever happened.
The source material we're looking at here has the perfect way to describe this. It really is like editing a photocopy. You can scribble all over that copy, change whatever you want, but the original document, it's sitting back in the filing cabinet, perfectly safe and totally unchanged.
So how do we actually edit that original document? How do we make a change that sticks? Well, this is where our pointers come to the rescue. The solution is something called call by address, and it is our first pointer superpower.
Okay, now look at how this changes the whole game. On the right, you've got the call by address version. In the code, instead of passing the values, we're passing their memory addresses. That's what that little ampersand does. It's like giving the function a home address. Now look at the memory diagram. The pointers inside the function, x and y, aren't holding copies anymore. They're holding the exact location of our original variables. So when we use that little asterisk to dereference them, we're reaching right back into the main program's memory and swapping the originals. And this time, it actually works.
And that, right there, is the first superpower of pointers. It's the ability for a function to reach outside its own little box, outside its own local memory, and directly change data anywhere in your program. It's how you write code that has a real, lasting impact.
But just modifying data is only the beginning. Pointers unlock an even bigger, more fundamental power: the ability to manage huge amounts of memory.
You see, when your program runs, its memory basically has 2 main neighborhoods. First, there's the stack. It's a small, super fast, really organized little area where your local variables live. But the keyword here is small. If you try to create something too big on the stack, like a giant array, you can literally run out of room. That's a stack overflow, and it will crash your program flat.
So when the stack just isn't big enough, where do you turn? You turn to the heap. Think of the heap as a massive, wide-open pool of memory. It's way bigger, way more flexible, and perfect for large or complex data. But there's a catch. Unlike the stack, which cleans up after itself automatically, the heap is all on you. You have to manage it yourself.
And the tool that gives you the keys to this huge memory warehouse? I think you know where this is going. It's pointers, of course. This whole process is called dynamic memory allocation. Now, using the heap safely requires a strict 5-step discipline. First, you declare a pointer to hold the address. Second, you allocate the memory you need from the heap using the new keyword. 3, and this is so critical, you have to check if that allocation actually worked. If the pointer comes back null, it means the system is out of memory. 4, you get to use that memory. And finally, and you can never ever forget this, you must release that memory with delete when you're done. If you don't, you'll create a memory leak, which is a programmer's nightmare.
Okay, before we wrap this up, let's just quickly bust a really common myth. You'll hear this all the time, that an array's name is just a constant pointer. But as the source material bluntly puts it, that's just nonsense. A real pointer is a variable. It has its own space in memory to hold an address. An array name doesn't. It's just a label, a name tag for the starting address of that block of memory.
And that distinction is exactly why you can access array elements in 2 ways that look different but do the same thing. You can use the familiar square brackets, or you can use pointer arithmetic. Under the hood, the compiler often just translates that simple bracket notation into the pointer math version anyway. They're really just 2 different ways of saying the exact same thing. So let's just bring this all home. The key thing to remember is that pointers aren't about making things confusing, they're about giving you control. They grant you 2 incredible superpowers. First, call by address, the power to modify data anywhere in your memory. And second, dynamic memory allocation, the power to command vast, flexible memory from the heap whenever you need it.
So, once you start to see pointers, not as some tricky bit of syntax, but as a tool for ultimate control over your computer's memory, everything changes. The power is truly in your hands. The question is no longer if you can solve those really hard problems. It's what amazing things are you going to build now that you can. Thanks for joining us on The Explainer.